And now let's take a look at this definition again. In this definition, in order to define the measure preserving, we're using the measure directly. But recall that in measure theory, instead of using sets and measures, sometimes equivalently, we can use functions and integrations, because sets can always correspond to functions through indicator functions, and measures corresponds to integrals. And measures correspond to integrals. So there should be an equivalent definition of this in terms of the functions and integrals. And now let's talk about this. We will write this as a lemma. This is lemma 2.6 in the book. A measure mu on x is t-invariant if and only if we have the following equality of integrals. That the integral of f over x with respect to mu is same as the integral of f composed with t d mu over x for all f that are essentially bounded with respect to the measure mu. Remember that the essential supremum of f is defined to be, so first consider f when x ranges over the whole x minus a set, say n, and you take the supremum of this set. And now you take the infimum of this. We'll consider all possible n's that are null sets. And this infimum of supremum you get is called the essential supremum of the absolute value of f. And if this guy is less than infinity, then by definition f is in this collection. And that is the definition for L infinity. And now, moreover, if mu is t-invariant, then the equation 2.1 holds for f that is integrable. And the notation here is else mu is superscript 1. And the important remark here is that because mu is a finite measure, the set of integrable functions contains the set of essentially bounded functions. So L infinity is contained in L1. And remember, in measure theory, sometimes we'll identify functions. And remember, in measure theory or functional analysis, when considering this space, you usually put an equivalence relation in here to identify functions a set of measure 0, only differ on the set of measure 0. And that guarantees the well-definedness of those spaces as normed spaces. But here we don't have to worry about this too much, because oftentimes we will understand that those functions always defined modulo a set of measure 0. So we usually don't have to worry about those little details. Okay, anyway, let's prove this lemma. Proof is not hard. First of all, we prove this direction. Suppose 2.1 holds. Then, for any variable set b, we may take f equals chi sub b, which is the indicator function of b. It follows that mu of b is equal to the integral of chi sub b with respect to mu, and this, by our equation 2.1, is equal to chi of b composed with t integrated over x with respect to mu. And this is further equal to the integral of, remember by basic measure theory, this is same as the chi sub t inverse b integrated against the measure mu. And you should be able to verify this part directly. Those two functions are the same. And finally, this last part is equal to mu of t inverse b, again by the definition of the integral. And this proves that t preserves the measure mu. And this proves this part. For the other direction, we need the famous four-step argument. Recall that in measure theory, there's a very famous method called the four-step argument, that in order to prove an equality like this, where a general function and the integration are involved, we will first start with the indicator functions, and then we will pass to simple functions, and then non-negative functions, and finally general functions. And we are going to use this strategy here. And now let me make it more explicit. Suppose that the transformation t preserves mu. Then we look at this equation 2.1, this equality of two intervals, and this is what we want to prove. The first thing we could do is that we can prove this for indicator functions, where this b is taken from the sigma algebra. This is true because the left hand side is just mu of b, and the right hand side is just, you can easily see that this is mu of t inverse of b. And because we assumed that t preserves mu, then we know those two guys are equal. So this verifies this in the first step. So this is a step 1. And step 2, because simple functions are just linear combinations of those indicator functions, and it follows from the linearity of integral that we have The integral is same as integral on the right for any f simple. This is the second step. This is simply by the linearity of integral. Now the third step. For the third step, we're going to prove this for non-negative functions. Specifically, let f be an integrable function and the f is non-negative. And it should be understood that this is non-negative almost everywhere. And now we choose a sequence of simple functions increasing to f. So here it would be great if we change this notation f to s. So we should use s. In this step, we are going to choose the sequence of simple non-negative functions increasing to f. So you should have already seen this in measure theory. Then it follows that for this f, you have the integral of f composed with t is equal to the limit as n goes to infinity, s sub n composed with t, taking the integration. But now here, by the monotone convergence theorem in measure theory, you know you can pull this limit outside of this integral because of the monotonicity of s sub n. So this is really equal to the limit of this integral as n goes to infinity. Now let's look at this limit. So each term here, because we proved in our second step that this equation holds when s is simple, so here this limit will be same as the limit of the integral of s sub n integrated against mu. And this last integral, what can you do with this last integral? Again, you will use the monotone convergence theorem to move this limit inside. But you know, once you put this limit inside, the limit will give you f. So the last term, let me skip one step to just get the final conclusion that this is the integral of f. And this is what we want to prove. We just want to prove this is equal to this. Now we proved for the non-negative functions. The last step will be very easy because any integrable function can be written as its positive part minus its negative part. Remember, this first part is f plus f's value of f divided by 2, and the second part is f's value of f minus f divided by 2. And they are both non-negative, so that you'll be able to use this third step and the linearity of this integral to conclude that finally you will have this equality holds for any integrable function. And this finishes the proof. That's it.